Namaskar, myself Professor Jaimala. This is my another lecture on mechanics, which is based on conservation laws. First of all, we will derive the conservation laws for a single particle, and then we will extend these for the system of particles. As you know that uh, mechanics um, is the oldest branch of physics, and the main credit for the mechanics, specifically the classical mechanics, um, goes to Newton. Though the mechanics was started from the time of Archimedes, rather Aristotle. This was started from the time of Aristotle. It saw many developments, and then finally, traveling a long journey, it reaches to Newton. And it is true that Newton is neither the last nor the first one to develop the mechanics. Still, we say that he is the founder of mechanics because these are the laws of Newton's, or you can say this is the Newton who unified the terrestrial mechanics and the celestial mechanics. He provided a theory which was applicable to both, and the laws provided by him are assumed to be as the basis of mechanics. In the long run, the mechanics was developed, and it went to the relativistic mechanics, the quantum mechanics, and other branches of mechanics. But the basic branch, or which you can say the Newtonian mechanics, is the most important mechanics, in which the base is the Newton's laws. Actually, Newton, as all of you know, that Newton provided the three laws. The law of inertia, in which he says that in an inertial frame, uh, a system or an object will remain in its state of rest or in state of motion if unless and until some external force is applied on it. So it is his first law of motion known as inertial law of motion. And then he provided the second law, which is known as the law of causality, in which he says that the total forces working on an object are equal to the rate of change of momentum. Now, what is momentum? Momentum is mass into velocity. So he says that the change of momentum basically depends upon the forces impressed on it. Then he provided, this is the second law, in which he says that F is equal to ma. M is the mass, a is the acceleration. So I can also write it as mv dot or mv dot is representing the derivative or the change. Mv means the momentum, so it is momentum. So rate of change of momentum is equal to total force. This is his second law. Actually, it was the first time when the notion of force was given in a rigorous way. And it is also true that Newton told that forces are the cause of motion, but how the forces will work was not uh, predicted by Newton's laws, three laws. The third law of Newton is known as the law of reciprocity, in which he says that for every action there is an equal and opposite reaction. And it is important about this law that he does not say that the line of action of the force and the force of reaction will be the same. That may be the parallel, but the line will be the line will be the line joining the two is not predicted by him. He does not say. that the force exerted by one body to another body, and then in reaction the force exerted by the another body on the first body will work on the line joining the two. It is not predicted in his law. So basically he gave three laws, and then because these three laws were talking about the force but not about how these forces will work, he provided one another law which is known as universal law of gravitation, which is also a very famous law. In this law of gravitation, he told that how the force works between the two objects. And he told that if suppose we have two objects, one is exerting the force F12, it is the force exerted by first particle on second, then his law says that this F12 force exerted by one particle on the second particle will be equal to, by third law, F21, because the direction is opposite, and this again is equal to G m1 m2 upon R12 square. So it says that the force between the two, the force exerted by one particle to the other may be expressed in terms of the gravity constant. G is the gravitational constant, m1 and m2 are naturally the masses of the two bodies, and R12 is the distance between them. Here uh, G is the universal constant of gravitation, and it is clear from this expression that as the distance between the two particles will increase, the force of gravitation will decrease. So this is very important law known as universal law of gravitation, which uh, which provided the way how the forces will work between the two bodies. So these four laws finally became the base of the mechanics, which is known as classical mechanics. And uh, as I told you earlier, that in classical mechanics we study about the motion of a particle of an object which is classical. It is classical because it possesses certain characteristics, certain qualities, like it may be a point like object or it may be an extended object. The main thing is that its dimensions should be irrelevant to the motion. It should have the mass, electric charge, and position, because there I also gave you the concept of space, concept of time. And the important thing is that the object of Newton mechanics describes a continuous path in the space. So uh, first of all we will study that what are the conservation laws, or what how the conservation laws are produced. Actually these are the consequences of these Newton's laws. Whatever Newton provided through his theory are the four laws, basically are the four laws, and the consequences of the laws of these laws of motion are the conservation laws. Conservation laws are actually uh, these tell us about the constantness of certain property of a dynamical system. As I told you that initially I will discuss the conservation laws for a single particle, and then we will go for the system of particles. The reason being that Newton uh, Newton said that this this physical furniture of this universe is actually the composition of infinitesimal material points, and these material points are observed as particles. And whenever we talk about the extended objects, that simply means that that is the assemblage of these material points, or you can say the particles. So, if we want to determine the behavior of an object, naturally we will find the behavior of the particles of which this is composed of. And as I told you earlier, that the particle of Newton has mass, electric charge, and position. So we come to the conservation laws. As I told you that these are the consequences of Newton's laws of motion. Because if you, I'll prove it that how the Newton's second law or the third law make us reach to the conservation law. And basically these are powerful tool to solve many dynamical systems. And it is also true that these conservation laws tells nothing about the forces. Uh, so forces, or you can say that um, it is true that conservation laws are responsible for the motion of so many celestial as well as terrestrial bodies, but these conservation laws predicts nothing about the force. Okay, and this is the beauty of conservation law, that the planets move in their orbit. It is again because of conservation law. First of all, we come to conservation of linear momentum. So what is momentum? Conservation of linear momentum, naturally momentum in a line. So basically what is momentum? Momentum, if I am talking about the linear momentum, then physically you can say that momentum is the power of an object. Object is moving, so it is the power of a moving object which it can show on the another object to which it will meet in its course of motion. So it is the power of a moving object. Secondly, the conservation says that if I say if I talk about the momentum, first I talk about the momentum. If I am saying that there is a body which is heavy, and there is heavier than another body, like if you have a bowling ball as well as you have a uh, you have another ball of baseball. If I am saying that both are having the same momentum, both are having the different masses, one is heavier than the other, but if I am saying that both are having the same momentum, it simply means that the velocity of the heavier ball, that means of the bowling ball, will be less than the velocity of the baseball. Why am I saying so? Because momentum, if I define momentum, momentum is defined as, it is written as P mass into velocity. So it simply means if some body is of mass m1 and its velocity is v1, and another body is having mass m2 with moving with velocity v2, and I am saying that both of them are having the same momentum, but there is a difference of masses, between the two, m1 and m2, then it simply means that there should be a relation between their velocities. If it is heavy and it is light, then its velocity should be less than this v2. then in that case you will say that yes, the momentum is same. So I want to say that if two bodies are of different masses, then still their momentum can be same. Similarly, there is a concept that if I am saying that change in momentum, I am writing change in momentum. That means delta P. Mass will remain same and there will be a change in velocity, or change in momentum is equal to m. What is change in velocity? It is denoted by acceleration in time delta t. It is in time delta t. So it is a m delta t, or I can write delta p delta t is equal to, what is am or ma? It is force. So it simply means that change in momentum over a time is equal to the net force. So if there is a bigger net force, there is a bigger change in momentum. Or reversely, you can say if you want to find a bigger change in momentum, you will need a bigger force. I can give you one example. Suppose there is some obstacle or there is some stoppage where a truck is to stop as well as a car is to stop at the same stoppage. Both are coming with the same speed, but since the mass of the two are different, so naturally the momentum of the truck will be larger than the momentum of the car, and therefore because the momentum of the truck is larger, a large force is required to bring the truck to stop. So this is another concept, that to bring a larger change in momentum, a larger force is required. There is one another very interesting example about the larger force. Uh, you have seen that in modern technology, there is a concept of airbags in four wheelers. So if you are having a car of having the modern technology, that means having the airbags, then what is the role of those airbags? Suppose your car collide with someone, with some object, and when it collides, then your body, that means the body of the driver, is still in the same momentum. It is moving with the same velocity. It is because of the conservation of momentum. Even after the collision, it will move with the same momentum. And therefore, if the time is increased, if the time of collision is increased, then again the force is decreased. You can see from here, time of collision, if this time is increased, then naturally force is decreased. So how this principle is applied in practical problems, that when a driver is, when a car is colliding with something, then driver will not collide with the same speed or with the same momentum with the windshield, because the airbags will be opened, and then because of the obstacle created by the airbags, the time of collision with the windshield of the driver will increase, and therefore the force will be decreased, and the accident, the damage of the accident may be reduced. So that is why the airbags are fitted in the cars, to prevent, or to, or you can say that to decrease the damage of accident. So this is again the concept of force related to momentum, or the time related to momentum, change in momentum. Now we see that Suppose you are having, I have told you that if I am having a mass m1 and another mass which is uh, another object whose mass is m2, like, but the relation between m1 and m2 is that both are same. Suppose this is coming with some velocity, say v1, and it is also coming with some velocity, say v2. So what is the total momentum? mv1 plus m2 v2. These two bodies collide with each other, and after collision, suppose these repel, then the law says that the momentum will still remain preserved. It may happen that the velocity of one body may be aggravated, but simultaneously the velocity of the another body will be decreased. So the law of momentum says that if before the collision the momentum was m1 v1 plus m2 v2, even after the collision it will remain the same. Again, if you are having the two bodies of different masses, then the same thing may happen. It is of m1, it is of m2. One is moving with velocity v1, another is moving with velocity v2. Both collide, and after collision, suppose they repel. So if the situation is that before collision their sum of momentum is 0, then after collision this will again remain 0. These examples are showing that momentum is in x direction and again it is transferring in x direction. It is true that both are repelling, so both the directions are opposite, but it is the transfer of momentum in x direction. It may also happen that when your one body is colliding with some another body, and I should make it like this. This is some another body, and let it moves, and after movement it comes to this position. This body, second body, may be in movement or at rest, and after collision this goes in this direction and this goes in this direction. So you see, here is a movement in x direction as well as in y direction. Here is a movement in x direction as well as in y direction. But basically, before the collision, there was only movement in x direction. So what will happen in this case? Transfer of momentum is in x direction and transfer of momentum is in y direction, but momentum in y direction for first body plus momentum in y direction for the second body will be 0. You can see that both are having the opposite directions and the momentum will be same in the two directions, and because the direction is opposite, so when you add the two you will get 0. The reason being, the conservation of momentum says that if before the collision there was no momentum in y direction, it will remain the same even after collision. That means even after collision the momentum in y direction will be 0. Similarly, if you add the momentum in x direction of the first body and momentum of second body in y direction after collision, it will remain the same as momentum of first body plus momentum of second body before collision. So whether the body repel or the body after collision move in the same direction, momentum remains conserved. And therefore it is said that in the universe, uh, all the objects are in random motion, but still the momentum is conserved in each and every direction. And it is, as I told you earlier, that it is only due to this conservation law that our planets uh, move in an orbit, and they move in a disciplinary way. Now we come to the conservation law for a single particle, for one particle. For that, we know that Newton's law says that F1 is equal to F2. I am talking about a one particle. Conservation of linear momentum for a particle. Okay. Actually, from here, I am giving you one concept. Then after that, I'll go to conservation of linear momentum for a particle. The first thing which you should keep very clear in your mind, that by linear momentum, we are concerned with the motion in a line. When I write F1 is equal to minus F2, this simply means that F1 means mass of first particle and its velocity, and F2 means mass of the second particle and its velocity, that is V2. Oh, sorry. Force means rate of change of momentum. So it is change of momentum of first particle is equal to change of momentum of second particle. Now what is P1? P1 is mass into velocity of first particle, and it is P2. P2 is mass of second particle into velocity of second particle, or M1 ddt of V1 is equal to minus M2 change of V2. M1 A1 is equal to minus M2 A2, or A1 upon A2 is equal to minus M2 upon M1. From here we get a concept. The concept is that the ratio of accelerations of the two particles which are interacting particles is constant. This is a constant. So ratio of acceleration of two particles to interacting particles. Interacting particles in an isolated system is constant. And what is its value? It is inversely proportional to the ratio of their masses, because here it is A1 by A2 and here it is M2 by M1. So this is one concept which is related to the Newton's third law of motion, law of reciprocity. Further, to prove or to find the conservation of linear momentum, we will start with uh, rate of change of momentum is equal to total force. and this gives m dv dt is equal to ma, and secondly you can write m is equal to p dot. Now suppose force is 0, then this implies p dot is 0 or p is constant. So it gives us one result. What is the result? If forces working on an isolated system are 0, then momentum, rather linear momentum is conserved. You may also see one more result. Suppose S is some vector along a line element and F dot S is 0. What does it mean? That force is perpendicular to that line vector. Force is working in the direction perpendicular to that line vector, and this implies what is F from 2? F is P dot. This is P dot dot S is equal to 0, or P dot S is equal to constant. Now what is this? What is this P dot S? P dot S is component of momentum in the direction of S. And it says that if there is no force in the direction of a line element, then momentum in the direction of that line element will be constant, is constant if there is no force along S or along a line element. So this is the conservation of linear momentum. Here I have given certain examples in which, in this example, you can see there is a big fish who eats a little fish which is at rest, and by calculating their velocities you can very well judge that momentum will remain conserved, because initially the momentum of the smaller fish was 0, while the momentum of the bigger fish was there because there was the velocity of the two. But as the bigger fish eats the smaller fish, their mass will be increased, but corresponding velocity will be decreased, and therefore the momentum will be conserved. Similarly, in the next sheet you can see that the bigger fish was at rest and the smaller fish was in motion, but when the smaller fish goes into the mouth of the bigger fish, that will start moving in the same direction in which the smaller fish was moving, and again the mass will be increased but the velocity will be decreased, and so momentum will remain conserved. Similarly, you can see in another sheet that there was a brick which falls with the 0 velocity, so its momentum was 0. But when it is loaded onto the cart, then because the mass is increased, the velocity is also adjusted in such a way that momentum will remain conserved. This is another example. Similarly, you can find so many examples on internet where you can prove that in practical situations the momentum is conserved. So finally we come to the conclusion that if the total forces in a direction vanishes, the linear momentum in that direction is constant in time, and that is the linear momentum is conserved. So this is all about this lecture. Thank you so much.